Everybody, Dr. Doyle here, and I am here to talk to you about flowcharts. And flowcharts are another way to represent algorithms. So we've spent some time writing algorithms and translating those algorithms into computer programs. And now we're just going to learn a different way to represent our algorithms rather than just a list of words. So a flowchart is a visual representation of an algorithm, and it really allows us to create an algorithm that we can go back later and look at and see it more visually, and more importantly, help to communicate that algorithm to someone else using a visual representation. And so it's just a different way to show algorithms that tends to help visual learners to process what's happening within your algorithm before we then interpret them into our computer program. Here's a couple quick examples. So first we have a flowchart for the song Hey Jude. Okay, so we have Hey Jude, don't make it bad. Anyway, you can go through and look through this. I just like this as an example. And then a perfect one for engineers. Here's an engineering flowchart, seeing if you need some WD-40 or some duct tape. So keep these in mind as we continue on through this quick lesson. So there are some conventions to keep in mind when you are creating flowcharts that are widely accepted as the symbols to use as you're creating your flowcharts. So some of this is going to be review for you from taking Intro to Engineering, for those of you who took that at Santa Clara University. So we're always going to start and end our flowcharts with an oval, and that just indicates that you're starting or ending a particular algorithm. You're going to have arrows, and these arrows are going to indicate the direction that your computer program or your algorithm goes, okay? We're going to try and make our flowcharts go from the top of the page down and left to right if we need more area, but you still need those arrows to indicate the direction. This parallelogram is going to be used for input and output, so you're going to use the parallelogram when you are requiring the user to input information into the computer program, but also when the computer program spits something out for the user to see or interact with. A rectangle is going to be used for any process, any assignment statement that you put into your computer program. It's going to be shown in a rectangle. And then the diamond is our decision, and we are going to be moving into working with decision statements here in the next couple lessons. So just keep this in mind, that the diamond is a decision where the computer program or your algorithm has to make a choice about which direction to go. So as we start to create some more sophisticated algorithms, and in particular with flowcharts, there are three basic control structures that we will use. The first one we've been using already, and it's just the sequence. And that's just when you do one process, then go to the next process, then go to the next process. These processes might require information from the previous one, so you might calculate a value v and then use it to calculate some other value z, for example, or they might be independent from each other. The next one, as I mentioned, we will begin to look at shortly, is selection. And this is going to require that decision, and it is basically going to allow your computer program to go down different paths based on if some condition is true or false. Within the selection statement, you may have sequence, what we call sort of embedded inside or nested inside. So just keep that in mind, that these can be combined. And then lastly, we have iteration. And iteration is just like it sounds. It's when you repeat a task over and over again. So this does require also that decision statement, that diamond, to see if you should continue on down the iteration path or move into the other path. So those three types again are sequence, number one, selection, number two, and iteration, number three. And we're still focusing so far on sequence, but we're going to quickly, I'm going to make another video shortly. My next video is going to be about selection statements and then iteration. So I'm going to go through two examples that we've already been looking at, just so you can get an idea of what translating our algorithms into an algorithm that is a flowchart might look like. So here was the area of an ellipse algorithm that we had previously used. We insert R1 and R2, then we set and solve A equals pi times R1 and R2 times R2, and then we output A. So what's that going to look like in a flowchart? Well, I'm going to start with that oval, and I'm going to just put the name of my algorithm inside that oval, so I'm calling it area of an ellipse. My next step, so this is again indicating my direction of flow, is to insert or input R1 and R2. My next step is to calculate A equals pi times R1 times R2. And then my next step is to output that value A, and then I'm done. So here is a flowchart representation of that same algorithm. And again, we could use either one, but again, this is the more visual and graphical representation, which helps people visualize what's happening. Our next step then would be to translate this into a computer program. We've already done that, so you can go back to the examples where we showed the area of an ellipse in MATLAB to remind yourselves what that would look like. Next, I'm going to do the example with the Skydiver. So here again was our algorithm. We're going to input m, the mass of the Skydiver, and t, the time that we're interested in looking at for the velocity. I'm going to assign some constants, c and g. Then I'm going to compute two values. First a, which is just an intermediate step where I calculate g times m divided by c. And then I use that to calculate v, the velocity, using the square root of that value a times the hyperbolic tan of the square root of a times t. Then I output the velocity. So here's what this is going to look like as a flowchart. Again, I'll start with that oval with the name of my algorithm, which may become the name of my computer program or user-defined function. And that's in an oval. My next step is to input m and t, and you can write these on two separate lines in two different parallelograms or combine them together, whichever one works for you. The next thing I'm going to do is set c equals 0.25. Then I'm going to set g equal to 9.81. Next, I'm going to calculate that intermediate calculation, a equals g times m divided by c. Next, I'm going to use that value a, and I'm going to calculate v equals the square root of a times the hyperbolic tan of the square root of a times t. Looks like I'm missing a parenthesis there, but that's okay. When I interpret it to my computer program, of course, my computer program is going to tell me if there's an error there. Then I'm going to output my value. Oh, this should say v. I'm going to output v, my velocity, to the user so they know what the ending velocity is. And then I'm going to include my end statement. So that's the information about flowcharts so far. So again, it's just another way to represent algorithms.